Action. I like Bing's picture today. Anyone like manatees? I like Anyone else like manatees? Nah. When I was a kid, I grew up out in the West Coast, and I think I was in 3rd grade. We took a trip to the aquarium in San Francisco, and I saw this exhibit with manatees, and I was like, whoa, those things are cool. And ever since then, I've had this, I love these things. I think they jokingly call them sea cows, right? Anyone ever seen one? In life? Real life? Yeah? Awesome. I'm jealous. This also makes me think of Florida, which, might be pretty good in the next couple days. Okay. So, we've model fit. We have 15 items. What does 90 represent up here in our likelihood ratio test? $90 degrees of freedom. 90 is also
number of degrees in a right angle.
very good. Very good. Number of degrees in a right angle. Very good. Right triangle. Well, which angle of the right triangle is the more? Anybody?
It's the difference between. In my head, I just can't get it out, but it's the model parameter.
It's the difference between. I'll start with that. What's the difference between? Very good. Parameters in the saturated model and whatever we specified. So, saturated model with 15 items. How many parameters do we have? 15 means? 15 variances? 15 times 14 over 2. What's this? 125? 135. 135. Okay. 135. Number of covariances? 15 times 7? No? What's this? 105? 105. Here, let me do this here. 15 plus 15, this is means, this is variance, plus 105 is 135, right? Is that what you were both saying? Thank you. And our model had 15 intercepts, 14 loadings, 15 unique variances, and 1 factor variance. So this is 15 times 3, 45. So 135 minus 45 is 90, which is that right there. You like that? You like me to quiz you on that real quick? No? Some people do, some people don't. I'm going to quiz you. Those of you who want to move the class along, answer. Those of you, that's a terrible idea. I want you to know this, and so if you have questions about it, know it. I want you to know where each part of this output comes from. We're going to focus on some things here. So this is our saturated model likelihood ratio test between saturated model and our model with 15 items, and we reject the null hypothesis. The null hypothesis here is that our model fits as well as the saturated model. It does not with the likelihood ratio test, but this being structural equation modeling, we have a pass, so we'll keep going. The CFI and TLI, CFI 0.909, TLI 0.894. Getting closer to good fit. I've seen things published with that. RMSEA now 0.053. Now that's pretty good. If I saw that, I'd be like, all thumbs up for you. Pretty close to less than 0.05. I'm all right with that. And the SMRMR, or the standardized root mean squared residual, at the bottom, 0.042. So we're starting to build a case that we have a 15-item scale that we're happy with. Now, advisors of mine, would you let me defend my dissertation? I'll go with Jennifer. Sorry, Jennifer. You were harsh before. Do I need to start over, or do you approve?
I don't think you should start over.
But maybe keep looking to improve?
But you could do a little better.
Oh, that's good. It's almost like you had looked at this lecture ahead of time. Thank you. Anybody else want to disagree? This is the great thing. When you have committees, if those of you who have had this before, you know what I'm talking about. If it's really good to get your advisors or your chair and your other people of the committees arguing with each other. They argue with each other and they don't bother you. All right? So that's my advice to you. Get them to discuss where they disagree. So does anyone like to disagree with Jennifer? No offense. We don't need to come to blows here. It's a, you know, anybody want to say this is a good fit? Good enough? That would actually be valid in a lot of journals. So, but I'm good. I'm good with going forward. I like going forward. I can look at the normalized residuals again. And if I do that, I see items 7, 16, and 18 had four significant normalized residuals. And the rest, items had 2 or fewer. So we got really good comparatively. I do think the choice of removal of additional items is ultimately up to theory or arbitrary. I'm just going to omit them to see how much better we can get. It's like limbo, but with items. How low can you go? Or RMSEA, for RMSEA, right? No? I'm trying to give up references that might be a little bit better than 300 or something like that. But I took out those 3 items. We now have 12 items. Oh, students, what does 54 represent in our likelihood ratio test for degrees of freedom? The difference between, I'm pointing at Devane.
Actually, I was trying to think of something with
54, no. Anybody know what a 54 is? No. Difference between the saturated model, number of parameters, and our specified model. So, again, our model fit is poor for the likelihood ratio test. But take a look. CFI and TLI are now up in the 0.95 area. Woot. You might get that PhD after all. Sorry. I say that tongue-in-cheek. My master's took 3 studies before I found anything with a significant effect. At which point, that one little thing, which was probably a type 1 error, allowed me to get a master's degree. All right, so this is probably where my bitter and cynical thing is. I promise, if I'm on your committee and you find a null result, I'm not going to make you start over. It's okay. It's what science. It happens in science. We just want the quality of the work to be good, right? So if I say that to you, please don't freak out about that. It's more just kind of you're hearing me being upset with my first advisor in grad school. I like the guy still. He was not my second advisor. Let's put it that way. Anyway. The P, so we got good CFI, TLI. The RMSEA is 0.043. Wow, that's pretty good. Jennifer, would you pass? Jennifer would pass me. Thank you. So now we have good fit. Now we can interpret the results. We spent 2 hours on fit and the results. Believe me, this is the way life goes. Hey, so here's some results. We have our standardized loadings on the left. I'm sorry, unstandardized on the left. This is with our marker item. Whoa, the way we can tell these are unstandardized is the first item. I should not even include the standard error in it. It's a 1, equal to 1. This standardized loading over here, stdyx, that's me leaving an M plus in there. This is what Levon calls std.all. Should be. So now, take a look at our loadings here. We've got our loading, we've got our residual variance. Some loadings are high, some are low. We could form a walled test with each of the loadings where we have a standard error, which is the loading divided by the standard error. Because we have good model fit, we can now look at items and see if we have a 0 loading or not. If there's a 0 loading, we would get rid of the item. It doesn't measure the factor, it's just adding noise. But we don't. We can keep all of the items. The residual variances, we don't do a lot of hypothesis tests with those, but we could. We just don't. Standardized values themselves. And our R squared, which talks about the proportion of variance in the item scores that's due to the factor. Variation in the factor itself. So, there we go. Some R squares are higher than others. So item 9 in the R square of 0.587, item 14 had 0.159. All of the items seem to fit, or at least they fit well enough for us to keep using this scale. But if we really wanted to look at maybe, if we had more than 24 items to begin with, maybe we'd come up with a better version or reword item 14 to make it a little bit better measure of the factor itself if we could. I don't have it in front of me for us to do that exercise. And take a look at our parameters now. For the 24 items, here are each of the 10 criteria and how many items were written to measure those. And now look at those. We have omitted criterion 9 and criterion 10. Those two, now we can't really say are part of our gambling scale. Right? Does anyone remember what those criteria happen to be? I think I have them here. I'm on slide 29. There we go. Jeopardize or lost a significant relationship, job, or educational or career opportunity because of gambling, or relies on others to provide money to relieve a desperate financial situation caused by gambling. So our gambling factor doesn't include these facets. Not directly. We're not asking about those directly. Now, if this gambling factor is supposed to be related to those, it's plausible we're still indirectly picking up information on that. It's also plausible that the DSM is garbage. Or it's not just plausible, I think it's confirmed. Is that right? So it could be that these two things are it's like Captain Obvious in the DSM. Yeah, they've screwed up their life because of gambling, they might have a problem. Right? So, but that's where this scale is going a little bit. Questions?
So shouldn't you feel pretty bad about having to have the number of items on your scale to get your model to fit? I mean, that just seems
Yeah.
Bad, probably.
Yeah, it feels really bad.
Yeah.
The reality of it is, it's so hard to get a scale to fit well. Any scale to fit well. But this is the process that has to happen. And in theory, the scales that you use would have already gone through this process. Or better yet, if we were really doing this as an exercise, we wouldn't just have 24 items to start. We'd have 150. And then we'd come down. Maybe we'd have multiple forms of this 12-item scale or something along those lines. But yeah, it's not, I don't feel good about it.
And follow-up question, I guess.
Yeah.
Isn't it somewhat unsurprising that they all have meaningful loadings, given that you just took out all of the crappy items?
Exactly. It is almost entirely unsurprising. In fact, it's rare when I see a factor loading that's not significant. It is almost impossible for that to happen. What that really means, if a factor loading is not significant, is that there's no correlation between that item and the factor, but then it's like that item's uncorrelated with the rest. If I were to throw in a random number to make the 13th item, right, we would still get good model fit, but we'd see a 0 loading on that random number. That's it. Yeah, it's very rare. So we don't usually think about that very often. Yeah, Megan?
Why did you use the marker item instead of setting
I will always use a marker item.
even for now?
From now on, the reason for it is because the standardized solution would be what I get if I would set the factor variance equal to 1. Right? These numbers would be my factor loadings. So with a marker item, I get both. I get unstandardized and I get standardized. And furthermore, if I want to go and use this scale in a subsequent analysis, I have an estimated factor variance that can be changed later on. But if I set that thing equal to 1, I can't use this in its entirety. But I could, if I would have done that, the results would be identical. The only difference is I just wouldn't have this column or this column. In this class, we will always do marker items because ultimately the goal of this class is to not actually do anything with the scores from the scale. We're going to build a simultaneous analysis where our factors are part of a path model. So to do that, we need to have their variances as estimated things. If we set it equal to 1, we no longer have estimated variances. Yeah, Devane.
So with this whole cutting the thing in half to make it fit,
Mhm.
as I said, make it fit 1.
Yeah. Mm-hmm.
If you tried to go publish that, wouldn't somebody say did you ever try seeing if there's more than 1 something?
You would hope they would, yeah. The reply to that would be, yes, but we're really looking just for 1. So 1 makes much more sense. I don't know. Yeah, it's an argument that would be based on what it is, what pathological gambling really represents, what the theory behind the trait is itself.
And then follow up
Mhm.
to that. With the whole, you said at the start of class, you had to have 3 items measuring a factor for it to be valuable.
Identified, yep.
So the 12 count doesn't have 3 items on anything.
Oh, no, it has 12 items on the one. There's only one factor here, and it has 12 items for it. Does that make sense? So if we only had 3 items here, imagine this is a scale with only 3 items, 1, 3, and 5. We'd have a factor, but it would be indistinguishable from just having all 3 items in a multivariate sense. We have 12. So this factor is identified by the number of items.
Okay.
And then plus the idea that we set the mean and we estimate the variance. Does that work?
Yeah.
Cool. You bothered by my comments? So you may see, and actually I learned it this way, where you estimate everything that we do in other contexts, we have this set to 1 right here. And that's fine if all you want to do is output the score and use it somewhere else. The purpose of this class, and actually the nice thing about SEM in terms of methodology, is that tells us when you output the score and use it somewhere else, you're just throwing all the error back into it, right? Build it into a simultaneous analysis if you can. If you can't, I'll show you a couple methods for that in a couple weeks also. But we'll get to it. So. Okay. Let's see here. There. Here are the final items on the scale. I like item 23. I gambled to improve my mood. I teach SEM to improve mine. No, that's not true. No, I mean I do get it improved. I'm fired up after class. That's why. Although I think my behavior after class is going to change this week. I don't think I'll be out at the bar, coming up with kids' names. No. Here is a path diagram of the analysis model itself. These are the standardized solutions. So one thing I wanted to do in gearing up toward talking about a little bit more about the factors themselves and building scales. Invariably, when you report a scale that you use in the study, you got to report their reliability. Again, this class is about using the simultaneous analysis of SEM, so we wouldn't need to report the reliability unless we're doing something with the scale or unless somebody asks for it. So I won't talk about reliability today, but part of reliability is related to this idea of item information, which is that each item of this scale is contributing information about a person's score on the scale itself. How much information it's contributing can be quantified. It can be quantified by something called an information function. So the information function comes from calculus. We can figure out, if we take our model right here, put it into our likelihood equation, and we take the second derivative with respect to the factor itself, we get an answer to this information function. What we end up seeing is the information function for a CFA, for an item, is the squared loading over the residual variance. Right? This is a number that characterizes an item. Each item will have an information amount. Right? The higher the information, so the actual number itself means very little right now in terms of what we do. But in a relative sense, some items will have more information than others. Right? So take a look at this function first. The factor loading squared over the unique variance. Well, here's the factor loading. That is like the covariance between the item and the factor. And so we know that the bigger the loading, the bigger the covariance between the two. But this function gets big when the size of the loading is big relative to the size of the unique variance. Right? So unique variance is what's left over in the item that's not accounted for by the factor. Right? So big loadings are one thing, but it's big loadings squared really, it makes it bigger, over the unique variance that talks about it. So item information is key because each item has an amount of it, right? We can say if we had this, we didn't just have 12 items. If we had, you know, a huge amount of items, maybe we wanted to create different test forms. We'd want our test forms to give the same amount of reliability for each person. So we would construct a form and try to get the item information to line up so that the reliability would be comparable. If you've taken the GRE, did you take it, most of you took it more than this last year, right? The new GRE, a little weird. The old GRE, not the old. I took the old GRE, pencil and paper GRE, but the one that was not where the scale was 130 to 170, 180, you know what I'm talking about? The old on the computer. That was something called an adaptive test. You've heard of those before? An adaptive test relies on item information also. It tries to pick an item that's the most informative for you. If you've taken item response theory, that's where that terminology comes from. It's still an information function. It's still found with the second derivative using calculus. But the information function is different because the distribution is different. So what we're taking the derivative of is a different function. And in the information function shows up the factor itself. So information is a function of the factors. So some items are more informative for people at different levels of the factor, which enables the use of a computerized adaptive test because some people, it can shorten the test form. If you're at a high ability person, you only take items that are informative for your high ability. If you're, in this case, it'd be like having a person with high gambling tendency. We only give them the items that were really informative at that point. But with a CFA model, all items are equally informative across all points on the scale, which makes a computerized adaptive test a bad idea, because every item, the item that's most informative for you will be the same item that's most informative for anybody else. Always. So item information in CFA doesn't get talked about enough, or at all. I don't think it needs to be. But when you take, if you take item response theory, if you've taken the computerized adaptive GRE, you'll hear that's a reason to switch to IRT. Oh, we can adapt the test. Really, the information function is the same. The difference is the distribution. If you were to make a comparison, if you could choose, if you could truly measure an item with a quantitative number versus something as a yes/no answer like you would on the GRE or using item response theory, the information function is always higher, or the reliability is always more for a quantitative item than it is for binary. That's because if this now our items aren't truly quantitative; these are categories. But if you could somehow have an item that's measured in precision with decimals, you'd want to have that. Yeah.
So when you're looking at business stuff not
Mm-hmm.
you can look at the loading, can you also look at the information?
Yeah, absolutely.
Would you choose one over the other?
Either one is sufficient. I would usually look at the loadings if I have multiple forms I want to construct. So I would say, you know, this is the total information of the items on this test. I'd add up all the information, and then this other form, or this one form, this other form, I need to make that same number for. So you mix and match items so that the forms would be roughly equal on information. Then your reliability would be roughly the same. But, so one of the things that IRT, it's kind of a straw man argument. We hear, oh, IRT, you can build an adaptive test. And really, your adaptive test has less information than you would with a quantitative item. The flip, though, is we probably shouldn't be treating these items as categorical, as continuous. There's no way that 6-point Likert scale follow a continuum. But it's an interesting, I find this, when you're in this program, if you're in my program, the REMS program, this is a really interesting point of contrast. Because each method that you see used sort of has to give a sales a pitch to be introduced and to stick. And IRT's sales pitch partially was, hey, look, we can adapt the test. In factor analysis, we can't, but you know. Interesting stuff. But here are the information functions for each of our items. And you'll note, the most informative, this GRI 9 here looks like it's the most informative. Its loading isn't the biggest, but the size of the loading compared to the size of the residual variance is the difference. I then actually went into the syntax and I created, remember the colon equal? Oh gosh, homework 3 again, rearing its ugly head. Colon equal in Lavon was when we defined our indirect effects using products of parameters. We can also use it to give us results like information. So I went and I gave every loading a label, L1 through whatever. I gave every unique variance a label. And then for every item I created the information. Item 1 just has the number 1 there. That is the marker value of 1. So all this is doing is just creating our information amount for each item, because it's just a function of the loadings and the residual variances. Now another thing I'm going to note is the item information, because it's a function of loadings and residual variances, we really can't use it unless we have model fit. Right? Because if we don't have model fit, the loadings and residual variances might be biased. So we may have the wrong number for information. How are we doing? Is this coming together a little bit for you? So. Yeah, so here's what it looks like in Lavon. Okay, this is my pitch about item information. Okay, let me wrap up and then kind of talk about this. What are the methods used? Throw out bad fitting items. Normalize covariances. What is item information? It's how much information about the factor each item is giving you. It's calculated by loading squared over residual variance. Let me do this. So factor analysis is an interesting topic to me for a number of reasons. Pretty much all of us use scales in somewhere in research. Or we're learning about methods to develop scales. Or to, those of you who are around, we may not use scales, we may just use the methods that we use on scales. So they're everywhere. And you'll see that there's the methodology that we're talking about here may not fit with how it's used in practice. Right? How many of you, when you use a scale, just add the items together? It's okay. Yeah, you add the items together, right? That's what we do. Right? In our REMS program, when we rely a lot on item response theory. It's this factor analysis with when we don't assume continuous data. Right? For that to get off the ground to be used, it had to combat the alternative. When we have items that are scored correct or incorrect, we can just add up the number of correct responses. There's your score on the test. It's what we do on the quiz every week, right? It just happens all the time. But every time we do that, realize we're actually implying a model with that. And what the methods I'm trying to teach in this class, how it fits with that, a lot of times what people will do with CFA is they'll use the CFA approach to go and see that we have the right dimensionality. We have one factor, for instance, or we have 4 factors, or however many some sort of one. And then they'll stop there and then go and take the items and sum them together. And believe it or not, the results will be roughly the same. The difference in terms of the factor score, right? What the F, if we were to give everybody an F from the model versus giving everybody a score from the sum of the items, the correlation, if we have one dimension, is like 0.99. It's really high. Where the issue comes in is the measurement error. When we're working with F in the model itself, we have compartmentalized measurement error into this residual variance term. So it doesn't filter into this factor that's in a simultaneous approach. So CFA helps you to build a sum score, and if you're using sum scores, please use a CFA ahead of time. That still doesn't get you away from the measurement error approach, which I will talk about in a couple weeks. There are ways to do analyses with some test scores. You'd have to give somebody more than one score usually, but it's an interesting approach. It's kind of like imputation for the factor. The factor is missing, right? So we want to multiply impute it across the range of scores it could be. Same thing with the test score. Is a comparison to some of the large-scale testing techniques you're talking about, like IRT. If you're studying the methods that we use in our testing program, CFA and IRT are almost identical, particularly for one factor, right? If we switch this assumption of residual variance being normal, we add a link function to this, this is the two-parameter logistic model, the 2PL. Right? It's the 2PL for normal data. So when you look at your testing programs, when you've gotten your GRE score is not the sum score. Your GRE score is the analog of F right up here. That's F for you. That's the factor. Right? So again, just like the sum score, F has error in it. Were you told how much error was in your F, in your GRE score? Not in your GRE report. You don't want to look those up. You can. It's online. There's a thing online that's supposed to represent it, which is actually inaccurate. But you can look it up, and it's not good. But that is always present. So when you deal with a score, I guess what I'm trying to deal with this, our methodology here is to tell whether or not we have one factor. But when we get back to some score, whether it's just F or whether it's a sum score, error still shows up. Once we give a score, error still shows up. So. On that note, there's another neat thing. Has anyone ever been told, don't ever use factor scores before? Okay, good. in the social sciences, psychology, for years and years and years, been a psych major myself, we've been told never use factor scores, never use factor scores, never use factor scores. And the reason for that, never use F, that's a factor score, by the way, we can give the person. The reason for that was that if you, for most of recorded history up until like the 1970s, all we had was exploratory factor analysis around. And exploratory factor analysis, when you have more than one factor on your test, you cannot find a unique factor score for each dimension. They're indeterminate. But when you do a confirmatory analysis, you can, and you do. So if you ever see that, you may be up against that sometimes. Remind people that their GRE score is a factor score. That usually gets people back into the right mindset. Oh, yeah, GRE is a factor score. Well, why do I use it in GRE but not over in CFA or something else? How we doing? So I guess what I'm trying to say is I want to, if you're adding things together, you're like the rest of us. Heck, your quizzes, your homeworks, everything I'm doing here, I'm adding things together. I'm assuming they're all one dimension. Right? There's not enough time in the world to not go and make some assumptions for it. What I want to do is help you with those assumptions so that you recognize it, and then hopefully with methods that will make what you're adding together and then maybe using be more accurate and be stronger. So that's the goal for this. Cool? I'm on the soapbox now, preaching. Sometimes, I don't know, when I was learning this, I felt like you take different classes and they'd be sort of at odds with each other, even though they'd almost be the same thing. You ever feel like that in some of your classes? Especially methodology, depending on who you take the methodology from. I'm like the weirdest person to take methodology. I'm always at odds with everybody else. I'm surprised they haven't voted me off the department. Yeah, that happens. That'll happen. Those of you first-year students, you'll give it till about year 3. No, you don't want to work with Templin. He's terrible. Don't put him on your committee. But I pity those who... Megan, you'll be finding another advisor. It's fine. But yeah, actually, you started with Lisa, so... Anyway, I want you to know that I'm trying to make it so that there's a little bit... I want to tie in all the different messages you may hear. Each of the messages has a context where a lot of the times the methods are used. And actually, we're bumping up against it with the question of marker item versus factor variance estimated versus set factor variance. Right? In the item response theory world, you almost never see a marker item, although you could. Right? So you'll start to see this a little bit more as you go through. But always think about those differences. Try to reconcile these. That's where I feel like knowledge really happens, when you start seeing a little bit differences. Why is it this way? Why is it that way? Why is it that way? I think you learn a lot trying to answer that question. All right, I'm done. Everything. Actually, do you have questions? No, everyone wants to get out of here. Leave. I'll see you later. See you next week. Thanks for your time.